Welcome back to ECE 320A. We're in the convolution unit, and what we want to do in this video is illustrate one of the strategies that I think help in terms of performing the convolution, and that is breaking the convolution up into sort of different parts. And one of the parts is learning how to flip and slide different waveforms, and that's this x of t minus lambda or h of t minus lambda, whichever convolution integral expression you're using. You need to get comfortable with flipping and sliding waveforms. That's what we want to do. In a subsequent video, we'll talk about intervals and limits, which is also an important part of the entire convolution integral process. But in this particular video, let's now talk about finding this functional expression x of t minus lambda and how we might do that in a procedural manner. Suppose that we're given x of t that looks like this different shaped object. We have a linear slope from t sub 1 to t sub 2. We're constant, let's say, from t sub 2 to t sub 3. And we have another distinct linear slope from t sub 3 to t sub 4. It doesn't really matter the shape, but I want to make sure that it's clear how those different parts are impacted when we flip and get ready to slide the waveform. Another important concept to keep in mind is we're going from x of t to x of t minus lambda, but in the x of t minus lambda expression, lambda is our independent variable, and it's the variable of integration in the convolution process. T is in fact an adjustable parameter that we allow it to move from minus infinity, which is way over to the left in our x of lambda or in our lambda axis, and it's way over to the right when we allow t to move closer to positive infinity. So we're adjusting t from minus infinity to infinity, and lambda is our variable of integration in the convolution process. And we're actually going to break up finding x of t minus lambda into three different steps. First is really the trivial step or the easy step, and that is to replace t with lambda. The next step is to actually flip x of lambda. We just found that in step number 1. We want to flip x of lambda around the vertical axis at lambda equal to 0. So here is lambda equal to 0. We now want to flip x of lambda about this vertical axis, and that's what I'm trying to indicate with this blue highlight. That's the flip, so that now we had, if just envision this as being a lambda axis, we're flipping t1 over to minus t1, we're flipping t sub 2 over to minus t sub 2, etc., so that now when we, in step 2, flip x of lambda around the vertical axis, we now have a minus t1, and then going from right to left, we approach minus t sub 2. Our function is flat from minus t sub 2 to t sub 3. And then we have that different slope down from the constant down to 0 from minus t sub 3 to minus t sub 4. Finally, then, we introduce the t parameter, which is an adjustable parameter, and that's the one that's going to allow us to slide this expression, this functional form, x of t minus lambda, through h of lambda when we're performing the convolution process. And we let t start as far to the left as necessary. That's close to minus infinity or close as we need it to be to obtain the first unique overlap pattern. And then we slide t through, or we slide t from left to right, and as we're sliding t from left to right, we're looking to find unique patterns of overlap between h of lambda and x of t minus lambda. That uniqueness of overlap, that will be in the subsequent video, which is talking about intervals and limits. But in this particular video, let's just focus on creating this functional expression, x of t minus lambda, in a graphical manner. And by now introducing the variable t, all we've really done is put a t in front of each one of these different variables on the lambda axis. We now have t minus t sub 1, t minus t sub 2, all corresponding to the same functional values as the minus t sub 1, etc. You can check your work if you now plug in t equal to 0 or t equal to any value, but t equal to 0, we already have that diagram or function drawn. That's now what this is. If you now plugged in t equal to 0 into this x of t minus lambda, you better get back x of minus lambda. So let's illustrate this three-step process with a few examples. Suppose now we start with one that's not very involved functionally. So here's t, and let's say this is now our x of t. And suppose now that functionally it has a constant value from 2 to 5, and let's just say that that constant value is 4. In the first step, so ultimately, what we want to do is we want to find x of t minus lambda. That's our goal. That's our end goal, and we're breaking that up into 3 different steps. Step 1 is to find x of lambda, and that shouldn't be difficult. All we're doing now is changing everywhere we had a t, we're replacing that with lambda, so that now x of lambda should look the same as x of t functionally. It's just now our variable is lambda instead of t. In step 2, this is the fun step. In step 2, what we want to do is we want to flip x of lambda into x of minus lambda. And that can be accomplished by, and the flipping is with respect to the vertical axis at lambda equal to 0. And if we now just flip x of lambda across lambda equal to 0 axis, then the 2 becomes minus 2. Same functional value that we had before, and the 5 becomes minus 5. Granted, my pictures maybe aren't very clean, but it's supposed to be a mirror image of x of lambda. This is now x of minus lambda, where we're flipping across lambda equal to 0. The final step in this 3-step process, step number 3, is to go ahead and introduce our adjustable parameter t. Introduce t as a parameter, and that's going to, this t is adjusted from minus infinity to plus infinity, and that gives us our sliding. We're now sliding this x of t minus lambda throughout all possible values of lambda to produce unique overlap patterns between x of t minus lambda and h of lambda. In this case, by putting a t in front of it, or introducing the t, and we put the t into it at a low enough or a negative enough value such that initially this t minus 2 is not overlapping anything that we had in h of lambda. Or if h of lambda is starting at minus infinity, it may always be overlapping, but we can now see how exactly it does overlap. We have the same value of 4. This is now our flipped and ready to be slid function x of t minus lambda. And you could, as I said before, you could in fact check your work if you now examine x of t minus lambda when t minus 2 is 0, then what do you have? Well, when t minus 2 is 0, so now we've slid it up, we've selected the variable t such that t minus 2 is equal to 0. That now says that when t minus 2 is equal to 0, or when t is equal to 2 in our eventual expression, we would have a picture that now looked like, oh, t minus 2 is 0, so that's right there, and this becomes, what's that value? Well, when t minus 2 is equal to 0, the leftmost side was starting at t minus 5, but now we're using t equal to 2. This now becomes minus 3. This has a 4, and now we have a picture, an instant, when x is evaluated at 2 minus lambda. That's a way to start checking your work and how this adjustable parameter t influences the process. Let's look at example number 2. In example 2, a lot of times we will be faced with exponentially decaying waveforms. Let's look at one of those. Suppose x of t is now given by 5e to the minus 2t. So that now we're starting at 5 at t equal to 0, and we're exponentially decaying with a decay rate influenced by that minus 2. And again, we have the same ultimate goal, which is to find x of t minus lambda. And we're breaking that up into 3 different pieces. The first piece, or 3 different steps or stages, the first piece is to find x of lambda. And again, that one's not hard. We're just replacing t with lambda, so that now x of lambda starts at 5, and your sketches can be much better than mine, but that's now supposed to be 5e to the minus 2 lambda starting at 5. That's x of lambda. Step number 2 is where we flip x of lambda around the vertical axis lambda equal to 0, or now we have, for lambda, this is now x of minus lambda. We still start at 5, and now we come down, and this now becomes 5. But what do we have? Now we've replaced lambda with minus lambda. We had 5e to the minus 2, but now we're replacing lambda with minus lambda. So this is actually going to be 5e to the 2 lambda, and you should be able to plug in different values of lambda and produce the correct functional value of x of minus lambda. Meaning, if you looked at maybe a value of x of minus lambda, so we have a minus, and then let's say that we have evaluating that at lambda equal to minus 1, then in fact that's 5e to the 2 minus 1, or this you could say is x of 1. Well, x of 1, when our functional form was 5e to the minus 2 lambda, then we get exactly the same result, and that's now what we would have had right there. So there's a check on our picture. Is it consistent? Does x of minus lambda look right relative to what we started with, which was x of t? We went from x of t to x of lambda, then to x of minus lambda. Now what we want to do is produce or introduce a variable t so that we can now shift this waveform from t equal to minus infinity all the way up to t equal plus infinity. In step 3 then, we are looking to find x of t minus lambda. In this case, here's our axis, there's 5, here's x of t minus lambda, and what we want to do is pick t such that it's far enough to the left to where we might not have any overlap between x of t minus lambda and h of lambda. This location right here is now related to that location there, except now we've adjusted it to where that's relative to t. That's now t. It was at 0. If we plug in t equal to 0, that will now shift it back over and produce x of minus lambda, which is what we want. And this expression now is found many different ways, but we could say, oh, that's 5e to the minus 2, and we're replacing t with t minus lambda. That's one way to find the functional expression. Another would be to simply return to x of t or x of minus lambda and plug in the expression for t. You should end up with consistency between the different functional forms for x of t minus lambda. Again, if we checked our work here, we could say at t equal to 0, we better get back x of minus lambda, which in this case we do. We now shift it over to where now we're on top of lambda equal to 0 with this exponential decay, where the exponential decay is now decaying off to the left, or as lambda approaches minus infinity. We've looked at a constant, we've looked at an exponential. Now let's look at something in between that may be a little bit more challenging actually, but let's now look at some linear waveform for x of t. So let's start with x of t. X of t, and now if I can sketch this properly, suppose this is now 1, 2, 3, 4, and maybe we now have, and like I said, maybe if I could sketch this properly, let's say that that is now where we have our expression defined or non-zero. So now I'm really going to be challenged to try to find my x-axis again, but this is now x of t. There's 1, there's 4, and we're now at minus 1. Here's minus 2. So this is, in fact, a straight line. And I hope you can see, well, it's not very clear the way I've sketched it because of my erasing from before, but now it's going from minus 1 to 0 over a span of 1, where we now have a slope of 1, so that now x of t now has a slope of 1, so it's 1t, and in fact, if we had the y-intercept, it would have occurred at minus 2, but we're only wanting this straight line waveform of x of t to be valid between t equal to 1 and 4. So there's now our x of t. It's now t minus 2. And it's true, or we want it to be non-zero between values of t between 1 and 4. So there's our expression and our picture for x of t, and we now want to find, again, we have our ultimate goal to find x of t minus lambda, and we're again breaking that up into 3 parts. First, let's find x of lambda. So now maybe I'm going to be challenged again to try to just sketch this waveform, this is now x of lambda. There's 1, 2, 3, 4. We're starting at -1, and we have a slope of 1 going up another 1, so that should be a value of 2. Here's -1, and this is now x of lambda is equal to lambda minus 2. And if we plug in any value of lambda between 1 and 4, we should land on this linear curve describing x of lambda. There's now our x of lambda equaling lambda minus 2. And again, that's only true between 1 and 4 for values of lambda. Now we want to flip that around the vertical axis, lambda equal to 0. Or wherever we were at 1, we're now at -1, and where we were at -4, we will be, where we were at 4, we will now be at -4. So we better be up here at 2 for when we evaluated at -4, and we better be at -1 when we are at lambda equal to -1. And hopefully you can see that if we mirror imaged x of lambda across the vertical axis, in fact we would find this expression, which is now, if we now look at x of lambda, we're replacing lambda with minus lambda, so this should be minus lambda minus 2. And if we evaluate that, or here this is now minus lambda minus 2, or this is minus lambda minus 2 as a functional form, we now have a slope of -1, and we have a y-intercept consistent with what we had with x of lambda. The y-intercept is now -2. And so we could now find this equation. We have a slope of -1, and we have a y-intercept of -2. So there's many different ways of finding that functional expression for x of minus lambda. Finally then, in step number 3, we want to find x of t minus lambda. And to do that, all we really want to do now is shift this x of minus lambda to the left by selecting appropriate values of t, so that now we have something that looks like t minus 1. It now goes up, and this is now t minus 4. This would be a value of 2. This would be a value of -1. And functionally, this is x of t minus lambda. So if we went back to our x of t and replaced t with t minus lambda, we would have t minus lambda minus 2, or this is now equal to t minus lambda minus 2, and you should be able to substitute in different values for t and lambda and end up with the appropriate functional value for x of t minus lambda. In our particular case, suppose we let t equal to 0. Then x of t minus lambda with t equal to 0 becomes 0 minus lambda minus 2, and that better look like what we would expect x of minus lambda to be. So if we plugged in t equal to 0, this will now slide over from what we've pictured to a value that looks like this particular graphic for x of minus lambda. If we now looked at a different value, suppose that now somebody wanted to really check our work, and we said, what's t equal to -1? Now, if we have a specific value of t, we can specifically mark that down. Now t equal to minus 1. Now we have minus 1, minus 2 for the rightmost endpoint. We're now at minus 2 for a value. And at that particular value, we need to be at minus 1. And at minus 3, we should be at 0. And at minus 4 and minus 5, by minus 5, we need to be up at 2. And now, depending on whether I've drawn this very accurately, but this is now a minus 1, this is 2, and this is now x of t minus lambda when t is equal to minus 1. And this particular functional form is now t, which is minus 1, minus lambda minus 2, and hopefully now, if you plug in different values of lambda between minus 2 and minus 5, you will actually, in fact, pin down that particular point on that functional description. And that's now what I would like you to be comfortable with in terms of flipping and getting ready to slide any of these expressions in our convolution process.